Opticks is a book by English natural philosopher Isaac Newton that was published in English in 1704. The book analyzes the fundamental nature of light by means of the refraction of light with prisms and lenses, the diffraction of light by closely spaced sheets of glass, and the behavior of color mixtures with spectral lights or pigment powders. It is considered one of the great works of science in history. Opticks was Newton's second major book on physical science. Overview. The publication of Opticks represented a major contribution to science, different from but in some ways rivaling the Principia. Opticks is largely a record of experiments and the deductions made from them, covering a wide range of topics in what was later to be known as physical optics. That is, this work is not a geometric discussion of catoptrics or dioptrics, the traditional subjects of reflection of light by mirrors of different shapes and the exploration of how light is bent as it passes from one medium, such as air, into another, such as water or glass. Rather, the Opticks is a study of the nature of light and color and the various phenomena of diffraction, which Newton called the inflection of light. In this book Newton sets forth in full his experiments, first reported to the Royal Society of London in 1672, on dispersion, or the separation of light into a spectrum of its component colors. He demonstrates how the appearance of color arises from selective absorption, reflection, or transmission of the various component parts of the incident light. The major significance of Newton's work is that it overturned the dogma, attributed to Aristotle or Theophrastus and accepted by scholars in Newton's time, that pure light is fundamentally white or colorless, and is altered into color by mixture with darkness caused by interactions with matter. Newton showed just the opposite was true. Light is composed of different spectral hues, and all colors, including white, are formed by various mixtures of these hues. He demonstrates that color arises from a physical property of light. Each hue is refracted at a characteristic angle by a prism or lens, but he clearly states that color is a sensation within the mind and not an inherent property of material objects or of light itself. For example, he demonstrates that a red-violet color can be mixed by overlapping the red and violet ends of two spectra, although this color does not appear in the spectrum and therefore is not a color of light. By connecting the red and violet ends of the spectrum, he organized all colors as a color circle that both quantitatively predicts color mixtures and qualitatively describes the perceived similarity among hues. Opticks and the Principia. Opticks differs in many respects from the Principia. It was first published in English rather than in the Latin used by European philosophers, contributing to the development of the vernacular science literature. This marks a significant transition in the history of the English language, with Britain's growing confidence and world influence, due at least in part to people like Newton. The English language was rapidly becoming the language of science and business. The book is a model of popular science exposition. Although Newton's English is somewhat dated, he shows a fondness for lengthy sentences with much embedded qualifications. The book can still be easily understood by a modern reader. In contrast, few readers of Newton's time found the Principia accessible or even comprehensible. His formal but flexible style shows colloquialisms and metaphorical word choice. Unlike the Principia, Opticks is not developed using the geometric convention of propositions proved by deduction from either previous propositions, lemmas or first principles. Instead, axioms define the meaning of technical terms or fundamental properties of matter and light, and the stated propositions are demonstrated by means of specific, carefully described experiments. The first sentence of the book declares, "My design in this book is not to explain the properties of light by hypotheses, but to propose and prove them by reason and experiments." In an experimentum crucis or critical experiment, Newton showed that the color of light corresponded to its degree of refrangibility, and that this angle cannot be changed by additional reflection or refraction or by passing the light through a colored filter. The work is a vade mecum of the experimenter's art. displaying in many examples how to use observation to propose factual generalizations about the physical world and then exclude competing explanations by specific experimental tests. However, unlike the Principia, which vowed non-fingo hypotheses or I make no hypotheses outside the deductive method, the Opticks develops conjectures about light that go beyond the experimental evidence. For example, that the physical behavior of light was due its corpuscular nature as small particles, or that perceived colors were harmonically proportioned like the tones of a diatonic musical scale. The queries. See main. The queries Opticks concludes with a set of queries, in the first edition. These were 16 such queries, that number was increased in the Latin edition, published in 1706, and then in the revised English edition, published in 1717. The first set of queries were brief, but the later ones became short essays, filling many pages. In the fourth edition of 1730, there were 31 queries, and it was the famous 31st query that, over the next 200 years, stimulated a great deal of speculation and development on theories of chemical affinity. These queries, especially the later ones, deal with a wide range of physical phenomena, far transcending any narrow interpretation of the subject matter of optics. They concern the nature and transmission of heat, the possible cause of gravity, electrical phenomena, the nature of chemical action, the way in which God created matter in the beginning, the proper way to do science, and even the ethical conduct of human beings. These queries are not really questions in the ordinary sense. They are almost all posed in the negative, as rhetorical questions. That is, Newton does not ask whether light is, or may be, a body. Rather, he declares, is not light a body? Not only does this form indicate that Newton had an answer, but that it may go on for many pages. Clearly, as Stephen Hales declared, this was Newton's mode of explaining, by query, reception. The Opticks was widely read and debated in England and on the continent. The early presentation of the work to the Royal Society stimulated a bitter dispute between Newton and Robert Hooke over the corpuscular, or particle theory of light, which prompted Newton to postpone publication of the work until after Hooke's death in 1703. On the continent, and in France in particular, both the Principia and the Opticks were initially rejected by many natural philosophers, who continued to defend Cartesian natural philosophy and the Aristotelian version of color, and claimed to find Newton's prism experiments difficult to replicate. Indeed, the Aristotelian theory of the fundamental nature of white light was defended into the 19th century. For example, by the German writer Johann Wolfgang von Goethe in his Farbenlehre. Newtonian science became a central issue in the assault waged by the philosophers in the Age of Enlightenment against a natural philosophy based on the authority of ancient Greek or Roman naturalists or on deductive reasoning from first principles, rather than on the application of mathematical reasoning to experience or experiment. Voltaire popularized Newtonian science, including the content of both the Principia and the Opticks, in his Elements de la philosophie de Newton, and after about 1750, the combination of the experimental methods exemplified by the Opticks and the mathematical methods exemplified by the Principia were established as a unified and comprehensive model of Newtonian science. Some of the primary adepts in this new philosophy were such prominent figures as Benjamin Franklin, Antoine Laurent Lavoisier, and James Black. Subsequent to Newton, much has been amended. Science also slowly came to realize the difference between perception of color and mathematizable optics. The German poet, Goethe, with his epic diatribe theory of colors, could not shake the Newtonian foundation, but one hole Goethe did find in Newton's armor. Newton had committed himself to the doctrine that refraction without color was impossible. He therefore thought that the object glasses of telescopes must forever remain imperfect, achromatism and refraction being incompatible.